Is Antonina Kolokolova, who is from Memorial University of Newfoundland, Canada, and there's the title of her talk.
First question, can you see the fonts, especially the white?
Yes, white.
Okay. Please let me know if something is unreadable, because... So, this is going to be a very informal talk about not the work done, but the work I plan to do. So please bear with me if something that I say is too non-technical or seems kind of strange. If you want to ask me questions, please do it any time, and I'll try my best to answer. So, the main thing that I want to be talking, and the main thing that I'm interested in this context is proving when certain proof techniques work and certain proof techniques don't. Or another way of putting it is what is the reasoning power in the complexity theory sense, and I will explain more what I mean by that, of various proof techniques. In the last few years, there were several workshops, and there was an excellent workshop here about a month ago on barriers in complexity theory and logic. The barrier results are usually the results that say that certain kind of approach cannot work, certain kind of things are not provable in a setting. Last time I was going to a barriers workshop, the chair of my department said, "Oh, you're traveling so much, so what is the workshop you are going to?" And I said, "Look, complexity theory is when we try to prove that we cannot solve certain problems. Barriers is when we try to prove that we cannot solve those problems." So that's the kind of proving that we cannot prove that we cannot do things results. So there were several results like that already. Some of them are kind of in that complexity of reasoning settings, some are not, kind of general results. Diagonalization, probably the most famous, from 1975, which said that questions such as P versus NP cannot be resolved by using diagonalization alone. Sorry, I should have said relativization. Recently, a few years ago, there was a similar one saying that even if you do arithmetization techniques where you look at booleans at certain values over integer fields, still you cannot resolve those questions. Natural proofs, another one, and every time somebody comes up with a new way of doing things, the first reaction is, let's push it forward as much as we can, but the second reaction is, okay, we've pushed it to as far as we could see, is it the limit? Can we really resolve something drastically more open in some sense than what we already proved? And in recent years, well, I guess not so recent now, from 2004, there were several very beautiful results based on the properties of expander graphs. Those results were essentially of the form of taking things that were, I'm not saying it right, I'm just trying to tell the general intuition, more or less taking things that were sort of known in randomized settings and de-randomizing them. It's not quite what they were, and not all de-randomization, of course, that we know can be done using expanders, but this is the general feel. And the natural question is, how far can we push those things? What kind of things can be proved using expanders? People were able to collapse some complexity classes. Symmetric log space was proven to be equal to log space. Can we collapse something else? Can we collapse non-deterministic log space to log space by extending this technique, or is it the limit? So this is the general motivation, and the work, which is work in progress, which is in the future plans mostly, is to really try to see what is the reasoning power of those expander-based techniques, what can be proved about expanders, what is the computational complexity of the concepts needed to argue about expander graphs. So let me just give you a few examples of things provable in the setting of bounded arithmetic and why bounded arithmetic was is kind of a natural settings to explore those questions. So bounded arithmetic is essentially taking theories of arithmetic such as Peano arithmetic and bounding them to argue only with concepts of low complexity. So think about Peano arithmetic that can only do induction over polynomial time computable objects. So this would be one example of a theory of bounded arithmetic. Or first order definable objects, even weaker. So for example, if you take Peano arithmetic that can only version of Peano arithmetic which is so bound that it can only talk about first order definable as in data complexity setting concepts, then you get a theory V0 in which you cannot, for example, prove that parity is a total function. For cryptographers among you, it may be more interesting in another result, or I guess there is a theory which loosely corresponds to polynomial time. It's a little bit more powerful than some other theories corresponding to polynomial time. It's a theory operating with essentially NP concepts. And if the theory, called S12, proves Fermat-Little theorem, then the proof of this statement gives you an algorithm, probabilistic polynomial time algorithm that breaks RSA cryptosystem. So out of the proof you can extract an algorithm because the theories are so constructive that will actually break RSA. And another example, the natural proofs barrier, which tells you that if powerful pseudorandom number generators exist, then certain techniques, natural techniques, cannot be used to prove circuit lower bounds. It originally was proven in a setting of bounded arithmetic, and there were several versions of this, all done in the setting of bounded arithmetic. It was done by Razborov, and then it was extended into the more well-known result by Razborov and Rudic, which talks in general about unprobability circuit lower bounds under the assumptions of existence of those generators. So any questions or comments about that? So let me talk a little bit more about expander graphs. So loosely expander graphs are graphs that have two contradictory properties. On one hand, they're very sparse. They can be regular degree 3 graphs. On the other hand, they're very well connected. They have logarithmic diameter. And those two properties make them behave sort of like pseudorandom objects. A walk in an expander graph is very similar to a walk in a random graph. A random walk converges to uniform distribution about as fast as you would expect in a random graph. If you take a set of vertices in an expander graph and see how many edges are going from this set of vertices to outside to the complement, it's roughly, the expectation is roughly the same number of edges as you would expect in a random graph, and so on. Yet there are explicit constructions which give you those objects, so that allowed people to use them to de-randomize things that were previously only known by random algorithms. So let me tell you about some of the uses of expander graphs. In complexity theory, probably the most famous is a proof that undirected connectivity in graphs can be done in ST connectivity and undirected graphs can be done in logarithmic space. It was known to be somewhere between a logarithmic and NL for a while, and people kept improving the constant. They were randomized results, but in 2004-2005, there were two beautiful papers, both using expanders in different ways, one by Omer Reingold and another one by Rosenman and Vadan, which both gave an algorithm computing connectivity in undirected graph in logarithmic space. About a year later, Irid Dinur gave a combinatorial proof of the celebrated PCP theorem, which gives the proof system for NP, and the previous proofs were kind of error correcting codes proofs. Hers is much more combinatorial and also uses expander graphs. And another result, which is a fair bit older, but also quite useful, is monotone sorting networks. So AKS sorting networks are monotone logarithmic depth formulas which take their input and sort it. So essentially, the inputs are string of zeros and ones, for example, and the output is the string which has all the zeros in front and then all the ones. The fact that this is a monotone formula allows it to be used in some very interesting proofs. For example, when symmetric log space was not known to be equal to log space before Reingold, AKS sorting networks were used to show that symmetric log space is closed under complementation. And there are some interesting proof complexity results following from being able to formalize AKS sorting networks, but I'll talk about it later. So yes, expander graphs are very nice objects. Your first question is, do they even exist? Well, we wouldn't be talking if they didn't. A random graph is an expander with a high probability. Well, if a graph is sort of looks like random, then when you pick a random graph, it sort of looks like random with high probability. There are several explicit constructions. Yeah.
This is random with what distribution? I mean, no, obviously not constant edge probability, because then you get dense graphs.
Yes. So if you take a random 3 regular graph, so you pick a vertex and how do you do it?
You pick a subset,
yeah.
3-element subset.
Yeah. Then you get the high probability of expander. Yeah. Very good question. Thank you. Any more good questions? So let me tell you just one of the possible definition of expanders, and then I'll show you some examples. So yeah, there are constructions. Most of the constructions are algebraic. Actually, the best constructions are Ramanujan graphs based on Cayley graphs, but there are also combinatorial constructions, although the analysis uses algebra. So where does the name expander comes from? One of the properties of those graphs is if you pick a set of vertices, any set of vertices, and look at its neighborhood, then its neighborhood is relatively large. Of course, if you pick almost all of your vertices, you cannot expect to have a large neighborhood, but say if you pick any set which is less than half of the graph, you can expect the neighborhood of this set to be fairly large, such as constant fraction of the size of the set itself. Pretty much equivalently, you could say that every set you pick has many edges going to the outside of the set. Any set of vertices will have a lot of edges going to the outside, and the expansion as edge expansion is defined as the minimum over all set of the ratio between the number of edges going out to the size of the set. So sometimes when people talk about deregular graphs, when they want to make it even kind of more uniform, they normalize it by the degree, but it doesn't really matter, the definition doesn't change that much. So let me give you a couple of examples. So there are two different, not really different, but somewhat different types of expanders. One type of construction gives you bipartite graphs that are expanders, pretty much in the sense that if you pick a subset of vertices on one side, then its neighborhood on the other side is fairly large. This is the kind of expander that you need for AKS sorting networks, and those graphs were defined by Margulis in, I think, 1979-ish, and then Galil gave an analysis of this construction. The analysis is quite complex. They have to go to continuous and Fourier analysis on a torus or something. So the construction is simple to describe. Every vertex corresponds to a pair of numbers, so you get n squared vertices on each side, and then you connect a vertex corresponding to a pair xy to 5 vertices on the other side, one of them is horizontal line, and then you have those ones. Again, to see that why this is an expander is a pretty complicated proof. Another example, which I took from the notes of Shlomo Hori, Nati Lineal, and Avi Vigderson, probably the main survey on expanders out there, works as following. So take a prime and take a group corresponding to that prime. Now make a graph with a vertex for every element of the group, and connect an element to the element -1, to the element -1 plus 1, and to its multiplicative inverse. So for example, for Z7, this would be the corresponding graph. Now the claim is that this graph is an expander. And again, the reason it's an expander, don't expect, well, maybe in this room there are people who can see it right away, but the proof is quite complicated. It uses the Selberg's 316 theorem and some fairly deep number theory stuff. So you see, those objects, they're easy to describe, but when it comes to proving their properties, it seems like the proofs that we know are quite non-elementary. So any questions about that, comments? Yes?
Yes, one question is the quality of expansion you get. If I remember correctly, and it's been a while since I looked at this, the provable expanders, they have much less of expansion than you get from a random graph, what you can get with.
Yeah. So Ramanujan graphs for which there is an explicit construction, I think they achieve pretty much the same parameters as a random graph. But in general, for most of those proofs, it's enough for your expansion to be a constant fraction. I think Ramanujan graphs get 1/2. I'd have to check. And it's from Lubotsky, Phillips, and Sarnak paper, which build the Ramanujan graph. I think it has Ramanujan graph in the title. I'd have to double check on the parameters, but I think it pretty much gets the optimal. Yeah. Very good point. So yeah, I guess I should have said that when we talk about expanders, they actually mean certain degree of expansion which is large enough, and large enough here would be constant expansion. So constant is enough for the proofs such as undirected statistic and activity in logarithmic space. Okay, so let me say a few words about bounded arithmetic, just a setting. It's following the setting from the book by Steve Cook and von Nguyen. It's two sorted settings, so think about the formulas as having string inputs, which are the actual inputs, and number inputs, which are sort of auxiliary indexing the strings. And all the quantifiers allowed in the formulas are bounded by a polynomial in the length of an input. So for example, if your input is a string of length n, you could have another string which is of length n squared, which computes something on that string of length n, but you're not allowed to have an unbounded quantifier. So we could use this idea to build theories of arithmetic for many complexity classes. The base theory is the theory for, you could say, uniform AC0, or which would be very natural if you're coming from finite model theory background. It's a theory corresponding to expressibility in first order logic. So just think about taking induction over first order definable concepts, and you will get the base theory, which is V0. Same as saying scale down Peano arithmetic to everything bounded and definable by first order formula. So this corresponds to data complexity of first order logic, and similarly it corresponds to complexity class uniform AC0. Now Steve Cook and von Nguyen found out very natural way of building theories of arithmetic on top of V0. Take a problem complete for a certain complexity class and add the totality of characteristic function for that predicate to your theory. For example, for non-deterministic log space, which is characterized by the problem of directed graph reachability, you can add an axiom giving you, say, existence of transitive closure of the graph, or just reachability. In this way, you get theories for various classes inside NP, both uniform classes, Turing machine classes, and circuit classes. And in particular, in this talk, I will mainly be thinking about the class for TC0 and the class for NC1. So TC0 is a threshold circuits, and the interesting things about threshold circuits is that this is the minimal level we know which can do all of arithmetics, which can do multiplication, which can do parity, and this is a minimal level for which we don't really have any lower bounds at all. And the class NC1 is a class for polynomial size formulas, and it's interesting because of well, all sorts of connections and well, polynomial size formulas are interesting by themselves, but for example, AKS sorting networks, the sorting network is essentially polynomial size formula. So you want to be able, if you can, to talk about it in a class corresponding to polynomial size formulas. So here are some examples how you could define those things. So the theory for TC0 you could define by saying that you could count the number of ones in an input string, which correspond to a threshold gate. For NC1 you could talk about evaluation of monotone formula on a balanced binary tree and so on. So now when we are asking what is the complexity of reasoning, what is the complexity of a certain proof, one way to talk about it is what is the complexity of the concepts we need to operate with in the proof to prove the result. Can we prove it with polynomial time concept? Can we prove it with log space concept? Is it sufficient to only have something like counting number of ones in the input, or do we need to do something like approximate counting, which actually takes us above NP? So just to mention another piece of motivation, again, Steve started a program of determining this kind of complexity for proving various theorems of mathematics. It's sort of a complexity analog of reverse mathematics setting, and the question you ask, given a theorem, suppose you could define the necessary concept in bounded arithmetic, what is the complexity of proving this theorem? What kind of theory in the hierarchy can carry out the proof, and what is the minimal such complexity? And I guess a piece of advertisement, there is a book that many of you know by Steven von Goyen, which has a lot of recent bounded arithmetic and a lot of work which was done in this framework. So there was a result a couple of years, I think, ago by Emil Irzabek, who was showing that AKS sorting networks, you could formalize modular existence of a family of expanders in a slightly extended version of a theory for NC1. The interesting thing about his proof and his motivation was that this would allow him to give polynomial simulation with monotone sequence calculus of a general sequence calculus. And he mentioned in his paper that given that we could prove the existence of those expanders that need for the AKS sorting network to work, we can carry out the simulations, so monotone is as powerful as general. MLK is the same as LK. Another question, also in the same setting, can we formalize those proofs about undirected ST connectivity being in log space using log space reasoning? So in a way you could think about it as is the fact that ST connectivity doable in log space is really kind of a natural property of logarithmic space, or does it come from using some quirky thing that we are allowed to do with log space? For example, if you change your definition of logarithmic space from being able to have logarithmically many constant registers to several big registers, constant number that can store logarithmically many bits each, then this proof doesn't quite go through. I'm not sure if that's been published. This I got out of conversation with Jan Johansson. So, as I told you right away, this talk is about work in progress. This is about something that I am trying to do and which I hope to have more to say by the end of my stay here. So thank you very much for getting me here. So what we are trying to do is to figure out what the minimal theory needed to show the existence of those expanders, to minimal theory that would allow us to carry out the proofs of undirected ST connectivity being in log space, the minimum theory that's needed to show the expanders with parameters needed to complete Emil Irzabek's work on AKS sorting network and monotone simulation. So some of the ideas behind the proof, when you look at expanders, first you say, okay, all you're talking about is number of vertices or number of edges coming out of the set. That should be easy to argue with. But one thing is that the proofs that prove the properties of expanders, they don't go through using vertex expansion and edge expansion. Instead, they use algebraic definition of expanders, which is the fact that if and only if your graph is an expander, then its second largest eigenvalue, well, let's talk about deregular graphs, then its second largest eigenvalue is a constant. So if you have a deregular graph, then your first eigenvalue is a d. Suppose it's connected and non-bipartite, then your second largest eigenvalue is essentially gives you your measure of expansion. And this is exactly the quantity that the proofs proving the property of expanders are talking on. In particular, the combinatorial constructions of expanders, such as the one used in Reingold's proof, all of their analysis is about properties of the eigenvalue. But in bounded arithmetic, talking about eigenvalue now starts seeming kind of strange. We could get away with only talking about things rounded up to polynomial, though, because there is a connection, relatively tight connection between the eigenvalue and the vertex and edge expansion, but the proof of that connection is again kind of complex. So since I'm running over time, let me just finish by talking about future work. One of the main things is really to figure out what is the complexity of those expander graphs, formalize the proofs using expander, and see whether this is a technique that can give us something more powerful than the techniques that we knew before. There are lots of settings in which expanders are being used, such as some cryptographic construction, and one of the questions was, can you prove something about expander that would help with those cryptographic applications? Both proving things using expanders is easy would be nice. It would help with AKS sorting networks, but independent results would be very interesting as well. Okay. So, any questions?
It's time for one or two more quick comments or questions.
What is the discrete Jordan theorem?
Discrete Jordan curve?
Yeah. Or if you know, I mean, yeah, I'm curious. I'll find out.
So if, please correct me if I'm wrong. So if you are on a plane and, so the discrete version is suppose you have a grid and your curve follows the side of the grid, then what is the exact statement? I remember the discrete part now, I don't remember the Jordan curve part. No, let me look it up and I'll probably be able to tell you right after the talk. I'm just blanking out of like the basics of it.
You can tell me tomorrow too. Don't worry.
Let's speak, okay?
Sorry.